Alrighty. Howdy, folks. Let's continue with the testing of series for convergence, those kind of problems. I gave you the basics of several tests that we have at our disposal to test for convergence. But now let's dive into working on quite a few problems. Like I say here, please refer to that 140 problems in the document. I'm going to upload a document called Series Problems1.pdf. There are 140 problems in it. My desire is for you to be able to know how to solve every single problem in that one. Oh, come on, that's way too much. Yeah, I understand. But it's fun. It's lots of fun. Okay. And once you get the hang of it, you will actually thoroughly enjoy it. And also, my recommendation is as you watch this video, keep that printed sheet of tests for series.pdf also with you, because we will constantly refer to the different kinds of tests. Okay. Now here is the idea. While we were doing integrals, we learned different techniques of integration, right? The substitution method, then integration by parts and trigonometric integrals, trig substitution, partial fraction decomposition, and all that. But eventually in 7.5, the problems in that section were just a hodgepodge. They just throw an integral at you and say, hey, figure out this integral. And that meant you needed to know which method to apply. Nobody's going to tell you to apply this specific method, right? It's the same thing here. In one of the sections, man, I can't remember if it's 11.6 or 7 or something like that. One of those sections, they just give you a series and say, test for convergence. And what I did is, if that is the case, why don't I just go ahead and take all the problems from all the series tests and just put them together and shuffle them up. That way we don't know which section this problem came from, so what technique to apply. And that is a better way of handling all of this once you get the basics of the tests down pat. Okay. All right. Without much further ado. Here is something that you need to know. There are four kinds of series that we looked at, and the four kinds of series we looked at are GHTP. I'm a big believer of mnemonics. So GHTP, G for geometric, harmonic, telescopic, P series. Right? Those are the four kinds of series. So the reason I'm saying this is, as soon as you see a series problem, test for convergence, ask yourself, hey, is this a geometric series? If it is, then we know that if absolute value of R is less than when the series converges, you're done. And if the series happens to be a harmonic series, we know the series diverges. Keep in mind, we are just trying to figure out whether a given series converges or diverges, right? Telescopic, don't worry about that one. P series, for example, sigma 1 over n square. Does that converge? Yeah, it does, because it's a P series. And why do we call it a P series? Because it's in the form of sigma 1 over n to the P. Right? Here, the P series test tells us that if you have a P series and P is greater than 1, that series converges. Less than 1 or equal to 1, series diverges. Right? Of course, P should be greater than 0. It's a totally different proposition if P happens to be a negative number. Definitely diverges. Anyway, let's not worry about the P being less than 0. So for the other, so we learned about that with regards to P series. Now, what tests are available for that? Again, I'm a believer of mnemonics. So I have a mnemonic called DICLAR, DICLARR, DICLAR. D for divergence, I for integral, C for comparison, L for limit comparison, A for alternating test series, and ratio, R is ratio test, and another R is root test. I didn't discuss root test, but it's not too difficult to understand once you understand what ratio test is about. Or if you look at the handout, you will understand what it is. So when I solve some problems, I will cover the root test also, right? So this is what I would do. Somebody gives me a series. I say, let me see. Can I apply divergence test to it? What is divergence test? I'll just take the limit of a sub n as n approaches infinity and see whether it is not equal to 0. If it is not equal to 0, I'm done. Test for divergence says the series diverges. End of the story. Right? It's a quick test that you can apply. And if not, then can I do integral test on it, right? If the integral looks pretty complicated, probably I wouldn't use that technique, and so on. So it's like you sort of use a trial and error method. You try the first one, it doesn't work, second one, and so on. Okay, so let's try to apply that kind of a technique with all these 7 tests and solve a few problems. Okay, determine whether the given series or converges or diverges by applying a suitable test. I might say test for convergence. It's the same thing. Okay. Now this one. Whoa, wait a minute. Can we apply test for divergence? Which means what? Take the limit of this. Well, the limit I want to claim is equal to 0. Limit of 1 plus n square over square root of 1 plus n square plus n to the 6th. That is actually equal to 0, I would claim. Why is that? Well, as I talked about in class, ignore the lower order terms in the top. So ignore 1 and n in favor of n square. So the top just becomes n square. Similarly, in the bottom, ignore the 1 plus n square under the radical, and you're left with the square root of n to the 6. Right? So square root of n to the 6 is just n cubed. So by ignoring the lower order terms, we are left with an n square on the top and an n cube in the bottom, which is 1 over n. Limit of 1 over n is 0. Well, since the limit of a sub n turned out to be 0, inconclusive, we cannot say the series converges. So the divergence test cannot be applied to this one. Let me also mention this. Had that limit not been 0, we could immediately stop. We can conclude the series diverges and be done with it. Okay? All right. But since it is 0, we got to figure out another way. And to me, a good rule of thumb is if this a sub n has polynomials and or radicals only, like we have at the top we have a polynomial, in the bottom we have a radical, you couldn't call the bottom, the denominator, as a polynomial because it's got a radical in there, right? Usually a comparison test, either the regular one or the limit comparison test, is a good option. Okay, now pull the handout out and take a look at how this comparison and limit comparison tests apply. Suppose sigma a sub n and sigma b sub n are series with terms with have positive terms. It starts with that, right? So our series is sigma a sub n, and we need to come up with sigma b sub n. So what is that sigma b sub n? And my suggestion to you is you choose your b sub n in the following way. Let b sub n be the highest term in the numerator over the highest term in the denominator. Okay, highest term in the numerator is just n square, and the one in the bottom is square root of n to the 6 or n cube. Okay, and so we will apply limit comparison with n square, which is sigma 1 over n. This is the idea. We will apply limit comparison test with sigma b sub n equals sigma 1 over n. Now, take a look at the handout. How do you apply limit comparison test? You figure out limit of a sub n over b sub n, right? Oh, by the way, sigma 1 over n diverges as a harmonic series. Our sigma b sub n diverges. We also need to know that. So let's figure out limit of a sub n over b sub n as the test requires as n approaches infinity. And so we do this. Well, now on the top, we multiply, you get n cube plus blah, blah, blah. The highest term on the top is n cube. The highest term in the bottom, ignoring the lower order terms, is also n cube. And so we have this to be equal to 1, right? Again, look at what the test says. If you have already established that a sub n and b sub n are positive terms, and limit of a sub n over b sub n happens to be greater than 0 and finite, which is what it is, we have 1 which is greater than 0 and finite, then either both series converge or both diverge. Sigma 1 over n, the b sub n, sigma b sub n here diverges, we know that. So a combination of that and the limit being equal to a quantity that is greater than 0 and finite means our series should also diverge. End of the story. So thus the series diverges. Cool? All right, let's look at another problem. Problem 50. Square root of n square minus 1 over n cube plus 2n square plus 5. I don't know about you, but I clearly see a radical and a polynomial. That's it. There's nothing else. So my suggestion is, again, let's apply one of these comparison tests. And preferably, I like limit comparison tests for the most part, but there are some instances where I choose comparison. So what should we pick for sigma b sub n? You remember? The highest term on the top, ignoring the lower order terms, over the highest term in the bottom, ignoring the lower order terms, right? Which means on the top we would have square root of n square, and in the bottom we'll have n cube. Would you agree? Yep. So sigma 1 over n square. That's it. We can apply limit comparison test, which again means we'll figure out limit of a sub n over b sub n. Oh, by the way, I keep forgetting. We need to mention sigma 1 over n square, okay? Your sigma b sub n, does it converge or diverge? Converges because it's a p series with p equals 2 greater than 1, right? Now let's figure out limit of a sub n over b sub n. What does this turn out to be? What does this limit turn out to be? Check this out. There are two ways of doing this. Well, on the square root of n square minus 1, as n approaches infinity, that minus 1 can be ignored. Okay, so ignore the minus 1 under the radical, and so we just have square root of n square, which is n, times n square. So n cube on the top, and again ignoring the lower order terms in the bottom, we just have an n cube. So, I did it this way. All right. Either way is fine. So what did I do here? Let me explain. Would you agree that we have n square outside of the radical here on the top? The square root of n square minus 1, but this n square is outside of the radical. If we want to take it inside the radical, is that possible to take something which is outside of the radical into the radical? The answer is yes, you can. But you better square this as it goes inside, right? So n square going inside becomes n to the 4. So we have n to the 4 times n square minus 1 under the radical, which is what this n to the 6 minus n to the 4 is. So here I just happened to do that and then ignore the lower order term n to the 4 and in the top and 2n square plus 5 in the bottom. Either one is fine. So that turns out to be 1 as well, and it's greater than 0 and finite. So both series converge or both series diverge. And since sigma b sub n converges, our series also converges. End of the story. Next, sigma n square over 2 to the n. 2 to the n. Ooh. So a good rule of thumb is when a sub n has r to the n or a factorial, ratio test is a good possibility. Let me tell you something. While I say this is a good rule of thumb, is a good possibility, doesn't mean every single time it works. You may have to be a little more clever sometimes and apply a different test altogether. So typically, when I see an r to the n kind of a thing, I try out a ratio test. Okay. So let's look at ratio test. Keep the handout next to you and look at what the ratio test says we need to do. The ratio test says everything hinges on limit of absolute value of a sub n plus 1 over a sub n, right? So what is a sub n here? N square over 2 to the n. A sub n is n square over 2 to the n. If that is the case, what is a sub n plus 1? Replace n with a n plus 1. So we have on the top n plus 1 the quantity square over 2 to the n plus 1 in the bottom, right? So that is exactly what I'm about to do. N plus 1 the quantity square. Under 2 to the n plus 1, I'll go ahead and write it as 2 to the n times 2 to the 1. A to the m plus n is a to the m times a to the n. So 2 to the n plus 1, I'll write that as 2 to the n times 2. And instead of dividing by a sub n, I'll multiply by the reciprocal 2 to the n over n squared. The moment I do that, you can notice that we can cancel the 2 to the n. And everything is just multiplying. So we can pull this 1/2 outside as a constant multiple, which can be pulled outside. And that leaves us with 1/2 limit of, on the top, n plus 1 the quantity square and the bottom n square. Again, if you expand the top and ignore the lower order terms, that just becomes n square. And so n square over n square is 1. So 1/2 times 1 is 1/2, right? Okay, we figured out limit of absolute value of this thing, and that turned out to be 1/2. So what does the ratio test itself say? If this limit happens to be less than 1, is that the case? Yep, it is. If it is less than 1, then the series converges, right? So series converges. Okay, that's how we do this problem. Let's pick another one. Okay, 10 to the n over n plus 1 times 4 to the 2n plus 1. Again, it looks like ratio test is not a bad idea because we see an r to the n kind of a deal, right? So let's apply ratio test, which means limit of absolute value of a sub n plus 1 over a sub n. Tell me, for a sub n plus 1, what's the top? Would you agree? 10 to the n plus 1, which is 10 to the n times 10. Cool. In the bottom, this n should be replaced by n plus 1. So that makes it n plus 1, which is n plus 2. So n plus 2 in the bottom. 4 to the 2n plus 1. So that n, replace that with an n plus 1. So 2 times n plus 1 plus 1. Right? 4 to the 2 times n plus 1 plus 1, which makes it 4 to the 2n plus 2 plus 1, which is 4 to the 2n plus 3. And 4 to the 2n plus 3 is what I wrote as 4 to the 2n times 4 cube. Cool? All right, and dividing by a sub n, I multiplied by the reciprocal instead. So n plus 1 times 4 to the 2n times 4 over 10 to the n. 10 to the n's cancel. N plus, 4 to the 2n will cancel. 4 will go with 4 square, and all of this just reduces to that. And what's up with the period up there? Please forgive me for that. Yeah, I think we're left with just 10 over 4 square, 10 over 16, or 5 over 8. And n plus 1 over n plus 2, that's just the limit of n plus 1 over n plus 2 is just the ratio of the leading coefficients, 1 over 1. So 10 over 16 times 1. So that's 10/16 is less than 1. The series converges. You're beginning to get a hang of this one. So it's just a matter of applying the test. Okay, let's see. Sigma sine 4n over 4 to the n. You see, what test? Hey, according to what I did in the previous problems, 2 problems, I see an r to the n, so maybe ratio test. Not such. I think it's possible, but that's going to be a pain. Ratio test, because of this sine of 4n, is going to be a pain. So, I want to propose a comparison test. Okay, a comparison test. With what? So the moment I say comparison test, with what is always the big question, right? With 1 over 4 to the n. So b sub n is going to be 1 over 4 to the n. Do we know whether sigma 1 over 4 to the n converges? Yes, we do. What kind of a series is sigma 1 over 4 to the n, which can be written as sigma 1/4 to the n? That's actually a geometric series with r equals 1/4. Absolute value of r is 1/4, which is less than 1. So sigma 1 over 4 to the n converges. Cool. And we'll apply a comparison test with that. You like the idea? But then be a bit careful here. Can we really apply a comparison test to this particular problem? With sigma 1 over 4 to the n, I'll claim that there is no issue with that. But if you want to apply comparison test with the a sub n being sine of 4n over 4 to the n, there is a small problem. Can you guess as to what the problem is? If you want, pause the video and see if you can answer it. Okay. Hint. Read the test carefully. What is the very starting point of comparison test? Suppose sigma a sub n and sigma b sub n have positive terms, or series with positive terms. Is sigma a sub n series with positive terms? No. Sine of 4n could be negative, right? So, strictly speaking, you cannot apply comparison test. But check this out. Notice that for comparison test, the terms must be positive, but the presence of sign causes some of the terms to be negative, and thus comparison test cannot be used directly. Ooh, what's up with that? Directly. Here is the idea. What if we consider sigma absolute value of a sub n? Look at how clever this is. We are going to look at sigma absolute value of a sub n. Well, how can you do that, or what does it do? Go back to the thing about absolute convergence. There is a theorem we learned about which says if sigma absolute value of a sub n converges, sigma a sub n itself converges. In words, the way it is put is, if a series is absolutely convergent, then the series is convergent. What does it mean? If sigma a sub absolute value of a sub n is convergent, then the regular series without the absolute value, sigma a sub n itself, is convergent. So we'll make use of that concept. And the advantage of that is, now if we consider that, then 4 to the n is always going to be positive in our context. N is always 1, 2, 3, 4, 5, 6 numbers like that, and 4 to the n for all those values of n is going to be positive. It's only the sign 4n which could be positive or negative. So absolute value of a over b is absolute value of a over absolute value of b, and I'm removing the absolute value around the denominator because denominator is always positive. So let's retain the absolute value on the top, absolute value of sine 4n. But now, could we apply comparison test to the sigma absolute value of a sub n? And the answer is yes, we can, because this is definitely a series with positive terms only. So we'll apply comparison test with sigma b sub n, like I said, sigma 1 over 4 to the n, which is a harmonic series which is a geometric series with absolute value of r is 1/4, which is less than 1, and therefore that geometric series converges. And for comparison test, it is fairly straightforward to compare absolute value of sine 4n over 4 to the n with a 1 over 4 to the n, right? Can I make this claim that this is less than 1 over 4 to the n? You bet. The denominators are the same, but we know that absolute value of sine 4n will occupy only values between, you tell me, what kind of values will sine 4n take? Absolute value of sine 4n. Sorry, let me go back. What kind of values will sine of 4n take? Values between -1 and +1. Would you agree? Okay, if that's the case, what kind of values will absolute value of sine 4n take? Think about it. Would you agree only 0 to 1? There cannot be any negative values. The moment you take absolute value, the negatives become positive, right? -2, when you take absolute value, becomes +2. -0.5 becomes +0.5. So absolute value of sine 4n is guaranteed to be between 0 and 1. And in fact, I made an argument that it cannot even be equal to 0. Sine of 4n cannot be equal to 0, cannot be equal to +1. So some value between 0 and 1. Okay, let's not get too much into that one. So the point is, we can definitely make this claim. Absolute value of sine 4n over 4 to the n is less than 1 over 4 to the n. So if sigma 1 over 4 to the n itself converges, the series with the smaller terms than that is guaranteed to converge. So by comparison test, this series converges. This series, let me be more precise. By comparison test, this series is absolutely convergent, but by the theorem, if a series is absolutely convergent, the series is convergent, and so we can say the series converges. Cool? Whew. Let's pick another one. -10 the quantity to the n over n factorial. Ooh. What test? I think if you say ratio test, I suppose we could apply ratio test. But I have a feeling I did not apply ratio test. Instead, I applied what do you think? What test do you think? The moment I rewrote -10 the quantity to the n as -1 the quantity to the n times 10 to the n. What do you think I did? Or what am I planning to do? A couple things. Would you agree that I can do this? Negative 10 the quantity to the n is negative 1 to the n times 10 to the n? Of course. Because negative 10 can be written as negative 1 times 10. And the whole quantity is being raised to n, which is what makes it negative 1 the quantity to the n times 10 to the n. AB to the m is a to the m times b to the m. That's the concept I used here. Cool. Now what kind of a series does this look like? Would you agree this is an alternating series test? Alternating series? When n is equal to 1, we have negative 1 to the 1, which is negative 1, 10 to the 1 over 1 factorial, 10 over 1. Negative 1, the quantity square, makes it positive 1, 10 square over 2 factorial. And negative 10 cube over 3 factorial, positive 10 to the 4 over 4 factorial. That's how this series looks. Positive, positive, negative, positive, negative, positive, negative, positive, like that. So this is an alternating series, and we can apply the alternating series test to this one. Okay. The second point I wanted to make was, notice how I said in the beginning, we could apply ratio test. If some of you came up with, hey, I want to apply ratio test because I see factorial and r to the n. You're right. You're absolutely right. But I'm saying we can apply alternating series test because this is an alternating series. The thing is, what's that American expression? There are more than one ways to skin the cat. Right? So there are more than one technique that you can apply, one test that you can apply to reach the same conclusion. Oh, you better reach the same conclusion though. Okay. So I'm going to apply alternating series test to this. So look at the handout on alternating series test. So this one says what? Alternating series test says what? You need to figure out what b sub n is. Is this in the form of either this a sub n? This a sub n, is it in the form of negative 1 to the n minus 1 times some b sub n, or negative 1 to the n times b sub n? Yeah, this is in the form of negative 1 to the n times b sub n, with b sub n being this stuff, 10 to the n over n factorial. Okay. Yep. See, b sub n must be greater than or equal to 0 all the time. So we will look at this as being negative 1 to the n times b sub n, with b sub n being 10 to the n over n factorial. That's the key. And limit of b sub n is limit of 10 to the n over n factorial. Cool? What in the world is limit as n approaches infinity of 10 to the n over n factorial? Okay, let me put it this way. Would you agree the top goes to infinity as n goes to infinity? Yep. How about the bottom? Will it go to infinity as well? Yep. So the top is going to infinity and the bottom is going to infinity. Typically, one thing we could ask in such cases is, which one goes to infinity faster? That's a simple technique that you could apply. Of course, you can apply L'Hopital's rule and all that, but do we know the derivative of n factorial? No, that's a pain. So we are not going to apply L'Hopital's rule for this one. Fortunately, we don't have to. Let's ask, which one goes to infinity faster? Usually we say exponential. Oh man, exponential goes to infinity really fast. Imagine 10 to the n, 10 to the 1, 10 square, 10 cube, 10 to the 4, 10 to the 5. Very rapidly it's increasing. So it's going to 10 to the n goes to infinity very fast. N factorial, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. Don't let that deceive you. Yes, it is true that initially factorial is doesn't grow as quickly, but if you can do this. What do you think 69 factorial is? Push it on the calculator. That is the highest number that you can highest factorial that you can calculate on your calculator, because that turns out to be something times 10 to the 98. 70 itself, the exponent goes beyond 100, and calculators usually do not display anything bigger than an exponent of 99. So 3 digits it goes, the exponent goes, and it says error. So 69 factorial itself is 10 to the 98, but 69, when n is 10, 10 to the 69 is a lot less than 10 to the 98. Or there's a better way to argue this. Argue what? That in fact n factorial grows much faster than 10 to the n. Here is the way. 10 to the n is nothing but 10 times 10 times 10 times n number of times we multiply 10, right? Now what in the world is n factorial? N factorial is n times n minus 1 times n minus 2 times n minus 3 times dot 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 all the way up to times 4 times 3 times 2 times 1. Okay, that's what n factorial is. So could we ask which one is bigger based on this way of writing? Well, start with the very last term. Okay, no, I should put it this way. Would you agree there are n number of tens on the top? So there are n terms on the top. How many terms on the bottom? Well, bottom also has n number of terms multiplying. The first term being n, the second term being n minus 1, and so on. We have n terms multiplying even on the bottom, just like on the top. And if we start to compare, the top wins out with the very last one. If you look at 10 is bigger than 1. Top term is bigger. 10 is bigger than 2. Top wins out. 10 bigger than 3. But that is true only when we get up to 10 in comparison with 10 in the bottom. But beyond that, the terms in the bottom are definitely bigger. This n, especially as n goes to infinity, we are looking at n being a very large number. This n is bigger than that 10, n minus 1 is bigger than the 10, n minus 2 is bigger than the 10, and so there are many, many, many more terms in the bottom which are bigger than their corresponding terms on the top, which is the top terms are just 10. So the bottom goes to infinity a lot faster than the top. As a result, we have a number being divided by a larger number, and the limit is just 0. All the discussion just to say that limit of this is equal to 0, ladies and gentlemen. Okay, what else do we need? Limit of b sub n is equal to 0 for an alternating series test. Usually, okay, and then we need to compare b sub n plus 1. Is that less than b sub n? Yeah, this n plus 1 factorial is bigger than n, so this is just 10 times. So I'll worry about that a little less. This part, for pretty much all the problems that you encounter with alternating series, the moment the limit is equal to 0, this condition is automatically satisfied. The b sub n plus 1 is less than b sub n stuff is automatically satisfied for the problems that you deal with. But as a mathematically accurate thing, you have to show this to be the case. So just make a statement like this and I'm a happy man. Okay, so we found limit of b sub n to be 0, and we have shown that b sub n plus 1 is less than b sub n for all n. And so, ladies and gentlemen, the series converges. In fact, for all n greater than some uppercase n. I don't worry too much about it. Maybe some other time if I need to, I'll point out why I say for all n greater than some uppercase n and not just for all n. Okay, cool. So this series converges. Let's pick another one. -1 to the n times n over n. Hey, wait a minute. That is clearly an alternating series, right? So we'll apply alternating series test. Piece of cake. What is, answer me. What is a sub n? -1 to the n times n over n plus 1. That is your a sub n. Cool. Is this in the form of -1 to the n? Is a sub n in the form of -1 to the n times b sub n? Or -1 to the n minus 1 times b sub n? You agreed -1 to the n times b sub n? Yep, it is. What is b sub n? N over n plus 1. B sub n is n over n plus 1. Cool. So what should we do for alternating series test? We should take limit of b sub n as n approaches infinity. Let's do that. What's this limit equal to? 1. Ratio of leading coefficient, same degree polynomial, both on top and the bottom. Alternating series test says we have to have the limit should be equal to 0 for the series to converge, right? So what do we conclude when the limit of b sub n is not equal to 0? Well, we can immediately switch to test for divergence. See if that makes sense. We will switch to test for divergence immediately. What is test for divergence? Take the limit of a sub n itself, including that -1 to the n. What would that limit equal? This is a bit of a challenging question. You need to pause and think about it and tell me. What is limit as n approaches infinity of -1 to the n times n over n plus 1? If you said limit does not exist, pat yourself on the back. You are absolutely right. What? The limit does not exist? Yeah. What we have discovered is that this n over n plus 1 itself will approach 1 without the -1 to the n. N over n plus 1 itself will approach 1 as n gets bigger and bigger. So what does -1 to the n times n over n plus 1 do? Well, it will switch between -1 and +1. For a certain n, this quantity would be -1, and the very next term would be +1, -1, +1, -1, +1. It just keeps dancing between those two numbers. So that means the limit does not exist, right? And so, limit does not exist. So what can we say about the series? The theorem says, the contrapositive of the theorem or the divergence test says, if limit of a sub n as n approaches infinity is not equal to 0, for what reason? We don't care. For whatever reason, if limit of a sub n is not equal to 0, end of the story, the series diverges. Right? Oh, I got, in some case, hey, I found the limit of a sub n. That turned out to be 1. Oh, okay. So you mean to tell me it's not equal, the limit is not equal to 0. Yep. Okay. Your series diverges then. Oh, but the limit does not exist. Okay. You mean to tell me the limit is not equal to 0. Yep. So series diverges. End of the story. Right? That's the cool thing about the series diverges. Maybe I should have said does not exist and therefore not equal to 0. Would have added a bit more clarity. Sorry about that. Let's look at this guy. Natural log of. Any thoughts? I want to say test for divergence. How? What does test for divergence require us to do? Take the limit of this as n approaches infinity. What's the limit of natural log of n over 2n plus 5 as n approaches infinity? Well, simple. This is a polynomial, first degree polynomial over first degree polynomial, so ignore the lower order terms, or the ratio of the leading coefficients, 1 over 2. Natural log of 1 over 2 is the limit. That's not equal to 0. Natural log of 1 is equal to 0, so natural log of 1/2 is not equal to 0. Right? What is it? What exactly is natural log 1/2? We don't care. As long as we know that it's not equal to 0, we are in a good shape. So, by test for divergence, this diverges. That's it. Nice and simple problem. Cool. Ooh, I like this one. 3 minus cosine n over n to the 2/3 minus 1. Any thoughts? Let me show you how we can approach this. Read that out. We recognize that sigma 1 over n to the 2/3 diverges as a p-series, right? P is equal to 2/3 less than 1. So 1 over n to the 2/3, we're not talking about all this series, it's just simply 1 over n to the 2/3, sigma 1 over that one diverges as a p-series. So if we can show that the terms of our series are bigger than the terms of this diverging p-series, we're done. We can claim that our series also diverges because our series' terms are bigger than the terms of 1 over n to the 2/3. Cool? Now, the question is, do you know how to show 3 minus cosine n over n, how this is bigger than that? Check this out. So let's start with, eventually what we want to do is show that this is greater than that, right? But I won't just jump to that one because that doesn't make any. The truth is, yes, this is bigger than 1 over n to the 2/3. But how do you say that? If you just simply make that statement, it doesn't make any sense. We have to logically proceed. And allow me to show you step-by-step process. Mathematicians use this kind of a technique a lot. Suppose I keep the numerator the same and change the denominator to only n to the 2/3. Can I claim that this quantity is... Ooh, I did that. Yeah, come on, Sammy. All right, let me put it this way then. Let me leave the denominator the same. What kind of values can cosine n take? Values between -1 and +1. Would you agree? Not exactly, will never be -1 exactly and never +1 exactly, but some values between -1 and +1, right? So if we allow this cosine n to have its maximum value of 1, then 3 minus that 1 is 2. Right? So you would be subtracting the biggest quantity of cosine n from 3. So that means it becomes 2. So, could you claim that 3 minus cosine n is guaranteed to be bigger than 2? Let me repeat that. Pay attention. Can we claim that 3 minus cosine n is guaranteed to be bigger than 2? Yeah, because if you subtract anything less than 1, you would get, say for example, 0.5. 3 minus 0.5 is 2.5. So the value of 3 minus cosine n would be 2.5 in that case, which is bigger than 2. If you subtract negative 1, 3 minus negative 1 is 4. 4 is bigger than 2. So definitely 3 minus cosine n is guaranteed to be bigger than 2. So we can say 2 over, this is greater than 2 over n to the 2/3 minus 1. We didn't mess with the denominator. Right? Keep in mind, our objective is to show that this quantity is bigger than 1 over n to the 2/3. Are we there yet? Okay. We have a 2. Is 2 bigger than 1? Yes. So can I jump to this must be bigger than 1 over? Oh, come on, Sammy. All right. So apparently I used some other logic before I jump to this one. So let's keep the 2 on the top. N to the 2/3 minus 1, right? Would you agree this is bigger than 2 over n to the 2/3? The answer is yes, it has to be, because with a minus 1, subtracting a negative 1 should be, this denominator is a smaller quantity than n to the 2/3 itself, and lower the denominator, bigger the fraction. Right? So this is definitely greater than 2 over n to the 2/3, because this denominator, like I said, is smaller than this denominator and the tops are the same. So this fraction is bigger than this fraction. Now, can I claim because 2 is greater than 1, this quantity should be greater than 1 over n to the 2/3? So notice how clever this is. Instead of just somehow stating, yep, 3 minus cosine n is bigger than 1 over n to the 2/3, we are showing a logical progression of how we can make that statement. And that is the key in this problem. So the moment we do this, what was the whole idea? The whole idea was sigma 1 over n to the 2/3 diverged. These terms are bigger than these terms, so this series also should diverge, is the idea. Cool? Cosine 1, the quantity raised to n. Any ideas? Hey, that looks like r to the n. Ratio test? Yeah, you could do that. But do we need to? Is that a geometric series with r equals cosine 1? But I don't know what the value of cosine 1 is, man. No big deal. Do you know whether it is going to be between absolute value of cosine 1 would be between -1 and +1? Yep. End of the story. This is a geometric series with absolute value of r is equal to absolute value of cosine 1 is less than 1. So, converges. That's it. What? Isn't it? Yep, that's it. Some problems are ridiculously simple like that. 3 stars. Now this is cool like you wouldn't believe. It's a pretty challenging problem. Now watch this. We will apply root test for this one. What does root test say? We need to look at the limit as n approaches infinity of nth root of a sub n, nth root of this quantity. What? What in the world is nth root of this, man? If I said that, would you agree with me? What happened to that nth root? Yeah, nth root of a. Nth root of a, is that equal to a to the 1 over n? Right? So, in our case, that a is n over n plus 1, the quantity raised to n square, and the whole thing we need to raise to a power of 1 over n. Right? Now, is that in the form of a to the m, the quantity raised to n, which is a to the m times n? So n squared times 1 over n is just n. So that's why this is just simply n over n plus 1 raised to n. Cool? All right. So what now? What's the limit of this one? I would be really impressed if someone can tell me what the limit of this would be. All right. Can I write n over n plus 1 as divide both the top and the bottom by n? So if I divide the top by n, would I get 1? And the bottom, n plus 1 over n? And of course the whole thing is raised to n. Can I make this claim? But 1 to the n is just 1. So by dividing the top and the bottom by n and writing it, we can write like this. Cool? Now what is this limit equal to? Still no idea, right? Check this out. Can I write this n plus 1 over n as n over n plus 1 over n? N over n is 1 plus 1 over n. So limit as n approaching 1 over 1 plus 1 over n to the n. Cool. Now, do you remember a special limit that we talked about? This one is a special limit. What would this equal? Limit as n approaches infinity of the quantity 1 plus 1 over n raised to n. That's equal to just e, that Euler constant e. So this is 1 over e. What's the value of e? About some 2.7 something. So 1 over 2.7 is less than 1. So therefore this series actually converges. Right. So that's a 3-star problem. That's a really good one. Okay. All right. If a sub n, so I need to show you this. All right, let's try to wrap all of this up and go with this one. If a sub n is 2 times 5 times 8 times times 3n minus 1, please pay attention to this part. This is I'm very, very likely to ask you a question on this one. Okay. What is a sub 1 if that is the case? So maybe I should ask you, what's a good way to teach this? What is a sub 3? What do you think we need to do to get a sub 3? I wonder if that's a better way. And my answer is let's see how I proceeded. Okay, I think looks like I said, what is a sub 1? To get a sub 1, we need to start multiplying. Yeah, pay attention to this. We need to start multiplying. The first term we multiply by is 2, and the second term is 5. Third term we multiply by is 8. So we keep on multiplying like this, starting with the 2, until we get to 3n minus 1. But n here is 1. So we start multiplying with 2 as the first term. We keep multiplying until we get to 3 times 1 minus 1, which is 2. What? We keep multiplying by starting with 2 until we get to 2. So we already got there. What do? That means stop. Okay? If you didn't understand that, don't worry too much about it right now. When we go to a sub 2, okay, what is a sub 2? Like I said, start multiplying, start with the 2, and keep multiplying until, let's figure out, and keep multiplying until what we should, where we should stop. So plug n equals 2 into this 3n minus 1. 3 times 2 is 6, 6 minus 1 is 5. So we should keep multiplying until we get to 5. 2 times 5. Now a sub 3, where should we stop? 3 times 3 is 9, 9 minus 1 is 8. So we should keep multiplying 2 times 5 times 8, and we stop when we get to 8. So we stop with this one. Are we cool? There's one more way of looking at it. To get a sub 1, you say is 2. What is a sub 2? Whatever a sub 1 is, which is 2, times 3 more than that. Right? 2 plus 3 is 5. So to get a sub 2, we take whatever a sub 1 is and multiply that by an additional number. And what is that additional number? Well, that additional number is 3 more than the last one that you have. Think about it that way. It makes life easy. Cool. Let's apply that to get a sub 3 according to that way of looking at it. What should we do? A sub 3 is whatever a sub 2 is. Just quickly go ahead and write down what a sub 2 is. 2 times 5. But now you multiply by an additional term. What is that term? 3 more than the very last term that you had. 3 more than 5 is 8. Right? What should a sub 4 be? Whatever a sub 3 is, so 2 times 5 times 8, multiply by an additional term. What should be that additional term be? That additional term should be 3 more than this 8, which is 11. 2 times 5 times 8 times 11 is the idea. Right? So think about it that way. You want to get a sub some number, you go to the previous one and multiply by an additional term. All of this is because I'm trying to get to what in the world a sub n plus 1 would be. Okay, so if we apply this concept of a sub 3 is nothing but a sub 2 times one additional number concept, a sub n plus 1 should be what? Whatever a sub n is. So just quickly, to get a sub n plus 1, quickly write down all of these terms, 2 times 5 times 8 times 3n minus 1. But be sure to multiply this by an additional term. What should that additional term be? 3 more than this guy. Meaning, add 3 to this 3n minus 1. You get 3n minus 1 plus 3 is 3n plus 2. So guess what? A sub n plus 1 would be all of this a sub n times an additional term, which is 3 bigger than the last term that you had, 3n plus 2. Okay, good. So Let's look at this guy. By the way, this 2 times 5 times 8 times dot dot dot, it's a kind of factorial. So we'll apply ratio test, and a sub n plus 1 for the top would be n plus 1 factorial, which can be written as n plus 1 times n factorial. And for the bottom, we just figured out what a sub n plus 1 would be, right? 2 times 5 times 8 and dot 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 times 3n minus 1 times 3n plus 2. And divide by a sub n, I'm multiplying by the reciprocal. So lo and behold, what happens is a whole bunch of terms. 2 cancels out with the 2, 5 with the 5, 8 with the 8, 3n minus 1, all the way up to 3n minus 1 with the 3n. So all these things go away, and all these things go away, just leaving 3n plus 2 here. N factorial, they cancel, leaving us with simply n plus 1 on the top and 3n plus 2 in the bottom. What's this limit equal to? First degree polynomial over first degree polynomial. So ratio of leading coefficients 1/3, which is less than 1. So this series converges. Cool? One of my favorite problems. Sine of 1 over n over square root of n. Let me just go ahead and tell you how to look at it. Apply limit comparison test with b sub n is equal to 1 over n square root of n. Okay. Let me add some clarity to this. If you have sine of 1 over n over a square root of n, look at that 1 over square root of n, right? Now what you want to do is, for b sub n, multiply this by another n in the bottom. Always, if you have a sine of 1 over n on the top, whatever is the denominator, square root of n, multiply that by another n. Now, what do I mean by that? I could ask a problem like this: sine of 1 over n over, say, n to the 3 halves. Right now we have n to the 1 half. So if we have sine of 1 over n to the 3 halves, like I said, for sigma b sub n, be sure to multiply this n to the 3 halves with another n. So choose this as your b sub n times n to the 3 half. Why? You will see why that we should do that in just a second. Okay. All right. So, by the way, what happens? Does this series converge? Sigma 1 over n to the sigma 1 over n square root of n? Yes, it does, because we can write this as n to the 3 halves. So 1 over n to the 3 halves is a p series with p equals 3 half greater than 1. Okay. So limit of a sub n over b sub n is limit of sine of 1 over n over square root of n and n square root of n over 1. And the square root of n's cancel, and you get limit of n times the sine of 1 over n. But we can write that n as 1 over n, so that we have this form: sine of 1 over n over 1 over n. Okay. Now, what in the world is limit of sine of 1 over n over 1 over n? Let me see how okay, good, I did that. Can I replace 1 over n with an m? 1 over n with an m. If I do, would you agree the top becomes sine of m and the bottom becomes m? Sine of m over m. limit as n approaches infinity of sine m over m? We cannot do that. We cannot say sine of m over m, but then leave this as limit as n approaches infinity. We should say m approaches. Oh, what's the big deal? We'll replace with m approaches infinity. Not so fast. Not so fast. If m is equal to 1 over n, what? M equals 1 over n. As n goes to infinity, what happens to m? M actually goes to 0. In fact, to be more precise, m actually goes to 0 plus, meaning, notice 1 over n looks like this, the graph of 1 over n. So the values are, as n gets bigger and bigger, the values of 1 over n are approaching 0, but they are staying positive. They are approaching 0 from the positive side. The y values is what I'm looking at now, right? So strictly speaking, we should say limit as m approaches 0 plus. I should add a 0 plus there. We're going to make use of this concept quite a bit. Okay, so now we can apply L'Hopital to this. This is sine of 0 over 0, which is 0 over 0. Apply L'Hopital if you want. Or there is a theorem that says limit of sine theta over theta as theta approaches 0 is equal to 1. So you apply that and you get 1. Okay. Limit comparison test. We got the limit to be 1, which is greater than 0 and is finite. And so either both converge or both diverge. So our series converges. Cool? Now pay attention. What did I say we need to pick for sigma b sub n? We need to pick, if this is sine of 1 over n on the top, we need to pick 1 over whatever is this denominator, multiply that by n, I said. Why do we do that? Notice when you apply limit comparison test, the square root of n cancels out with the square root of n, leaving us with that n. We want to be left with an n. Let me repeat. We want to be left with an n so that we can write this as that n, that leftover n, as 1 over n, and then apply this concept. So what I'm saying is, if this were to be, say, n to the 3 halves, so make sure that you have a n times n to the 3 halves over here as well, whatever it is, right? So that n to the 3 half and n to the 3 half cancel, and you are left with an n. Okay, and we can apply whatever we did here. That's the whole idea. So you should apply limit comparison test by choosing an appropriate b sub n for this one.